Hey physics peeps, we're going to look at problems that involve conservation of energy and work that's involved. Because many times we don't just roll up a hill, roll down a hill, or just have something drop straight down. Many times there's other things that happen to that object, like energy added or taken away. We're going to have two problems that involve that, and yeah, we'll get going with it. So this problem, it says a 2,000 kilogram car starts at the bottom of a hill with a velocity of 10 meters per second. When it reaches the top of the hill, 25 meters high, it is now traveling with a speed of 12 meters per second. How much work did the car's engine do on the car? So I'm trying to visualize what this is. So we got this car at the bottom of a hill. Okay, so usually it's useful to draw things out. You're not quite sure what's going on in the problem because really we'll end up figuring out more when we can visualize it. So we got this car at the bottom of the hill. Great. And it says that it's going at 10 meters per second. So it's kind of moving, and then it goes up the hill, and at the top of the hill, that's 25 meters high, it's now going at 12 meters per second. So it's going up. Okay, that's cool. And it asks how much work did the car's engine do to the car? Well, when we do these problems, we can set up a conservation of energy situation, or those LOL diagrams, where we keep track of the kinetic energy and the potential energy as this thing moves along. And at the very beginning, we were at the bottom of the hill. Remember that this is kind of like our before, this is our after. And when we say before, we mean before it goes up the hill, it's when it's right here. And it was moving, it had kinetic energy, but it's at the bottom of the hill, so it has zero height, and that means that there's no potential energy. So it's like all kinetic. But when we get up to the top of the hill, we are now having potential energy. In fact, we got a lot of potential energy. But we also have a lot of kinetic energy. In fact, we have more kinetic energy than what we had to begin with because we're actually going a little bit faster. But when we have this is a little different than what we usually just set up with conservation of energy, where it was like you just had one or the other on each side. But here, it's set up this way because work is actually going in to the system. And that's what this O is for. It's telling you how energy is going in. And we're actually adding energy or work. And that work is done by the car. So when we set up our problem, we could do that EK plus EP equals EK plus EP. But we can cross out the potential energy on this side because we didn't have any potential energy on that side, or before when it was on the ground. We can't cross anything out on this side because we have kinetic energy and we have potential energy on the after part, or when it's at the top of the hill. So this is what we have to keep in. But we know that work is being added in, and that, because it's added in, actually goes on this side of the equation. This is where you would put it. So we can set up the rest of it. They don't give us the energies. We have to use the equations for them, like that 1/2 mv squared, don't forget the squared, for kinetic energy, and the mass times gravity times height for the potential energy. But the work here, it usually is force times distance, but they don't even give us any of that stuff. In fact, they're asking us for how much work is done on the car. And this is going to be the thing that we're trying to solve for. So we can put everything into the equation and try to figure it out. Like here, we have 1/2. We could put 0.5 times the mass. They tell us the mass of the car. It's 2,000 kilograms. Times the velocity squared. Well, at the very beginning, the velocity was 10 meters per second. So I need to make sure that I'm keeping track of what that speed is and where it was at. But I also need to make sure that I square that velocity. And then plus, I don't have the potential energy, but I do have this work that went into the system. And that's what made these graphs kind of not work out the same way that they usually do. And equals our kinetic energy. It's 1/2, so that 0.5, times our mass. And our mass, it's still 2,000 kilograms. Times the velocity squared, but it's not 10 here because after, now I'm on the after side. I have to look at when the car was up at the top and it had a velocity of 12 meters per second. But I have to remember to square just that piece. And I'm going to keep track of all my other math signs. Plus, now my potential energy, I had that. It's the mass of the car, 2,000 kilograms, times g for gravity, it's 9.8, times the height, and it's now the height of the hill, and it's 25 meters above the ground, or ground level, that level, and so 25 meters. So this is my setup, and that's the hardest thing to get to. But if I do all the math on this, so I'm going to start over here, I'm going to start simplifying things, and I'm going to work my way to solve for this W. So I have 0.5 times 2,000 times 10 squared. So I'm going to do 10 squared first, 10 times 10, that's 100 times 2,000, that's 200,000 times 0.5, I get 100,000. Plus W equals, over on this side, now I have 12 times 12 times 2,000 times 1/2 or 0.5, and you get 144,000 joules. Plus, now I have to do this part, 2,000 times 9.8 times 25. I get 490,000 joules. So I keep whittling this down, and I can add these together now. If I do that, I will end up with 3, and I got 0 and 4, it's 4, 9 and 4, that's 3, carry a 1, I get 634,000 joules on this side, equals 100,000 plus the work done by the engine. To solve for the work, I need to undo this 100,000, and that's by subtracting 100,000 from both sides. That goes away. I get my work is equal to 534,000. Because I just solved for work, remember work is a transfer of energy. My answer is in joules. And that's how I solve this thing out. Okay? So that's that tip problem. But we're going to take a look at this next one. A 95 kilogram bicycle rider starts down the top of a 50-meter hill with no velocity. She rides with the brakes on the whole way down. The brakes on the bike do 30,000 joules of work. When the bicycle rider gets to the bottom of the hill, what is the bicycle's velocity? So again, when I set this up, I'm trying to visualize what's going on. So you got this bicycle rider. She's going to start going down a hill. That's a steep hill. And this is a poor rendition of a bicycle, but she's on a bicycle. And she's going to, she has no velocity. So I'm just going to write that up here. So not doing anything. But then she's going to go down the hill. She's going to end up down here in another poor rendition of a bicycle. But now she's probably moving fast, but she was braking on the way down. When I set up my energy diagrams, this LOL thing, and I can keep track of the kinetic and potential energies as this person's moving. And at the very beginning, she doesn't have any kinetic energy. She's not moving at all. Remember, we set these up where one is before, one is after. And when we say before, it's before she goes down the hill. So we're talking about right here. But then the potential energy, she has potential energy. She's at the top of this 50-meter hill. And so I'm just going to draw it like she has all this potential energy. When she gets down to the bottom of the hill, she's braking on the way down. She might probably have some kinetic energy, but probably not all kinetic energy because she was braking. How much this is, not sure. But I know for sure when she's at the bottom, her height is 0. So that means that the potential energy is 0. And where this kind of missing energy goes, it's because she's braking. It does this much work, but that's not going into making her go faster or into making her have more energy. It is energy that's coming out of the system. The brakes take away energy, so it's slowing her down. So I'm going to draw it like this, and work is coming out. And when I set up my problem, this EK plus EP equals EK plus EP. That's cool. I can cross out things that I know that I didn't have. Like before, we didn't have kinetic energy. Great. Afterwards, we know we didn't have any potential energy. Great. But then this work, because it was taken out of our system, I'm going to put it over on this side because the arrow is kind of telling you which side it goes on. And it's either going in on the system, it goes on this side. If it's coming out of the system, it goes on this side. But now I can start putting all my stuff together. They don't tell me all these energies, except they do tell me the work. That's nice. But I'm going to have to use my mass times gravity times height for this problem. This 1/2 times mass times velocity squared for this part. And the work, they already told me what it was. In some cases, I could do force times distance, but not here. They told me what it was. So I could just do plus this 30,000 joules of work. Cool. I can put it right in for the work. But we may have to put everything else in. Like the mass of this person was 95 kilograms. Gravity, I know what that is. It's 9.8. Height. She starts with a height before, that's where she had potential energy. The height was 50 meters for the hill. And then for my kinetic energy, I have this 0.5 times the mass. And the mass, that was 95 again, times the velocity squared, which the velocity, be careful, it's not 0 because we're talking about the after now. And when she's down here, and gee golly, they don't tell me what it is. But you know what? They are asking me for what that velocity is. And because I don't know it, and it's what they're asking us for, we just leave it as V, but don't forget the square. Because the square, you can't forget it. So here's the setup. And the setup is the hardest thing. But your task now is to actually go through and solve for that V. And so when you're setting these types of problems up, if they talk about something going down a hill, something going up a hill, awesome. We can set up a conservation of energy problem just like before in these LOL diagrams. But when work is involved, we have to just tell if work is going into the system or going out of the system. And that tells us which side work goes on the equation. And then we can use that in the setup and solve for everything. Try it out, and we'll see you guys later.